In this class, we are going to discuss different types of operators, or what type of operators we can consider as the real operator in quantum mechanics. So in that case, first one we are going to discuss is linear operator. So there are a set of conditions that we have to put in order to consider an operator as a good operator for our quantum mechanical operations. So here an operator A is said to be linear when for any two functions f and g. So for example, here it says that we have an operator A operator. It should be linear when A is acting on two functions f and g in such a way that A operator acting on the function fx and then gx. Here there are two constants. Don't need to bother about the constants. So it is acting on fx and gx. So we can write this as c1, the constants we can take outside, and the operator acting on the function. Okay, so this is what the essential condition. The operator should act on a function, then only it has any meaning. Okay, so the operator acting on fx, and then we have taken the other constant c2, and then a operator is acting on the other function gx. Okay, if this condition satisfies, that means the operator, if we write it like this, the operator is acting on both these functions in this way. Okay, and if it obeys, the operator obeys this kind of condition, it is what is called a linear operator. C1 and C2 are arbitrary numbers or constants, either complex or real. It doesn't make any difference if we take it outside. The operator d by dx is a linear. Okay, if it obeys this condition, d by dx c1 fx plus c2 gx. So here you are getting c1 into df divided by dx. It is acting on d by dx is acting on fx, then we get a df, and d by dx is acting on gx, then we are get dg by dx. So d by dx and the operator integral are also linear. So we have taken the Schrodinger equation, or we started the Schrodinger equation with a double differential. So d by dx is acting as a good operator, or we can consider that in the quantum mechanics. And integral is also acting as a linear operator, so we can consider that in the quantum mechanics. The square operator is a nonlinear operator. Okay, so why square is a nonlinear operator? So if we operate the function c1 fx plus c2 gx square, then what happens is the square of this function will come, and then additional term will also come. So that will not obey this particular situation, okay, or condition. Okay, so here when you do the squaring of this function c1 fx plus c2 gx, then we get c1 square, this will be squared, c1 square f square x plus c2 square g square x plus the additional function 2 c1 c2 fx gx. This is just like a plus b all square, and then so this function does not obey this condition, so this is not a linear, square is not a linear operator. Similarly, the operators square root, log, etc. are also not linear. Okay, so this it so happens that the operator occurring in quantum mechanics are all linear. Okay, so we are putting certain conditions for the operator should be can be used for the quantum mechanical operations. Okay, so we put this condition as it should be linear. And then we are coming to another kind of operators, that is the Hermitian operator. If we take a linear operator that satisfies a very particular condition like this, then it is what is called a Hermitian operator. So what is the meaning of this equation? Here integral, as we have already told, this is a linear operator, and a operator is also a linear operator. And if we actually this condition you are not familiar with, we will be discussing it in the next slides. Integral psi 1 star psi 2 d tau means there are two functions, wave functions psi 1 and psi 2, and then d tau, this is what is called d tau. D tau means dx dy dz. dx means a small change in x direction, dy means small change in y direction, and dz is small change in the z direction. That represents the three coordinates. Okay, so three coordinate means it is a three dimension. Okay, so in fact integral psi 1 psi 2 d tau means it is actually the probability of finding the electron. So we will discuss it in the next slides. So this is actually now if we discuss much about it now, you may not understand it properly. In the coming slides we'll explain it properly. Okay, so integral psi 1 star a operator psi 2 d tau equal to integral psi 2 a operator psi 1 whole star d tau. So this means that, as I told you, integral psi 1 psi 2 or integral psi 1 star psi 2 d tau means the probability of finding the electron. So here effectively a operator is acting on the function psi 2. Okay, then we will get a function. Okay, then we will get a function, and that may be psi 1 star psi 2. Okay, and d tau. Okay, and here a operator is acting on the function psi 1, so we get a function, so that will be maybe psi 1 star. Okay, so effectively we have two wave functions, psi 1 and psi 2, or the complex conjugate of that one, and that actually defines the probability of finding the electron. You may remember last class, now on we were going to discuss only the probability of finding the electrons by the uncertainty principle. Okay, so here for any pair of functions psi 1 and psi 2 in a set that describes the state of the system is called Hermitian operator. So psi 1 and psi 2 are the two wave functions, so it defines the set of the system. Okay, and hence the operator a operator acting on psi 2 part of the LHS, integrand indicates the result of a operator operating on the function psi 2, while a operator acting on psi 1 whole star part of RHS, integrand is called complex conjugate. That's what I told you. In the next slides you will understand it more properly. Here you just understand that this kind of psi 1 and psi 2 are two different wave functions. So either one wave function can be a complex conjugate of the other one. Psi 1 star indicates the complex conjugate. Okay, so here psi 1 star complex conjugate is there, and we get another wave function here, psi 2. And here psi 2 is there, and its complex conjugate is psi 1 star. It is here. Okay, and so this represents the state of the system, or the probability of the electron around the nucleus. Okay, and we shall see that the operators corresponding physically observable quantities, position, momentum, angular momentum, energy, etc., all these need operators in quantum mechanics are essentially Hermitian. Okay, so here again we are putting another restriction or condition to be satisfied for an operator to become used in quantum mechanics. Okay, so first one we told is it should be linear, and second one is a Hermitian operator. Okay, and now we are coming to another two operators like Laplacian operator and Hamiltonian operator. Okay, so Laplacian and Hamiltonian operators we are using in order to reduce the Schrodinger equation. Now this is the long form of Schrodinger time independent Schrodinger equation: di square psi divided by di x square plus di square psi divided by di y square plus di square psi divided by di z square plus 8 pi square m divided by h square e minus v psi equal to 0. So this is the long form of time independent Schrodinger equation. Now we have to reduce this equation by using two operators like Laplacian operator and the Hamiltonian operator. Okay, now let us discuss it, how we are going to reduce it. So this is the Schrodinger equation, and now I am going to split this part. So this is 8 pi square m e by h square minus 8 pi square m v divided by h square. So I going to split this to this side, and here I have written the split equation I have written here. Okay, And then what next we are going to do is you have to take this term 8 pi square me divided by h square psi is the total energy, and this whole term we have to take to the right hand side. Okay, so when we take this term to the right hand side, the plus sign will become negative sign. Okay, and then this will remain on the left hand side. Okay, and this term will be the same, so we have written this term, and then next is 8 minus 8 pi square m divided by h square v psi. Okay, and then the others RHS we are getting 8 pi square me divided by h square psi. Okay, now what I am going to do is multiply this whole equation by h square divided by 8 pi square m. Okay, so on both sides we have to multiply with h square divided by 8 pi square m. Okay, and then this side h square divided by 8 pi square m and in bracket the same term, and then when we multiply this term with h square divided by 8 pi square m, so 8 pi square m term will be cancelled and h square will be cancelled, so what remains is v psi equal to, here also the same thing happen, equal to minus e psi. So we consider this is equation 1, and then equation 1 is multiplied with the negative sign, then we get minus h square, so this term will become minus and RHS will become plus. Okay, now we are giving another condition as h by 2 pi equal to h bar, h by 2 pi equal to h bar, and then if you give h bar square is equal to square this term h square divided by 4 pi square. Okay, here we have h square divided by 8 pi square, and then 8 pi square means 4 into 2 pi square, so we have 4 pi square, so h square divided by 4 pi square time you take, then you give h bar square, and then what remains is 2m. Okay, so I have written it here minus h bar square divided by 2m, and then this term I have taken psi outside. Okay, so this will be in bracket and then v, and then psi outside equal to e psi. Okay, and then this term, this differential term is an operator. Okay, and then we reduce this into this form del square operator. Okay, so del square is it is what is called Laplacian operator, di square divided by di x square plus di square divided by di y square plus di square divided by di z square is the Laplacian operator. Okay, and then we write the equation minus h bar square divided by 2m del square plus v psi equal to e psi. Okay, and then we take this whole term, one Laplacian operator is here and the whole term potential energy term will also be there, and this whole term is another operator h hat. This is what is called the Hamiltonian operator, and if we substitute h hat here, h psi equal to e psi. Okay, and this equation is the reduced form of the Schrodinger equation by giving the Laplacian and Hamiltonian operators. Hope you understand it. So it's a usual practice to write it on the following form. So this term actually they have written it directly without doing these steps. So I have written all these steps in order to reach to this step. Okay, so this step is actually what we are getting it here. Okay, right, we are getting it here. Okay, this step. Then we have taken it here, h bar, h by 2 pi, all these things we have done. Del square is, this is del square is Laplacian operator. Okay, and then what remains is this whole term will become h operator or the Hamiltonian operator, and then we get the equation h psi equal to e psi. Okay, so v is the potential energy and m is the mass of the electron. Del square is the Laplacian operator, and it thus contains two parts. One is kinetic energy part, because it contains v. This h operator is a conducting kinetic energy part, and then total energy part, kinetic energy part, and then the electrostatic potential energy part. Okay, so it contains both parts. Hamiltonian contains both parts, and then it is evident that the Hamiltonian is an energy operator representing sum of the kinetic energy and the potential energy of the system. It is the operator for the total energy of the system. Okay, so total energy is E. So when h psi is acting on the function, wave function psi equal to, we are getting E psi. Okay, so this is the reducer form of the Schrodinger equation rather than writing it in the lengthy form. Next is eigenvalue and eigenfunction of an operator. Okay, so all these steps we are giving certain kind of restrictions and conditions in order to make the operator to be useful for the quantum mechanical operations. Eigenvalue and eigenfunctions of an operator. If an operator A hat, when applied to a function fx, gives the same function back but multiplied by a constant factor c. Okay, so here it is given A operator is acting on this function, then we are getting fx. Acting on fx, we are getting fx multiplied by a constant c. Okay, if this condition is satisfies, this operator is a eigenvalue equation. Okay, so this equation is called an eigenvalue equation, and fx is the eigenfunction. Here fx is the eigenfunction if it satisfies, and c is the eigen value. Okay, so if this function acting on this operator acting on this function, we are getting the same function back by multiplied with the constant. Okay, so when you look at this equation, Schrodinger equation, here you can see that the operator acting on the function, we are getting the same function back multiplied with the constant E, energy. Okay, so the Schrodinger equation is obeying the eigenvalue equation, or it is an eigenvalue equation, and psi is the eigenfunction and E is the eigenvalue. Okay, and h hat is the operator, right? Then the function fx is called eigenfunction of the operator A, and c is called the eigenvalue, and the equation is called eigenvalue equation. Okay, hope you understand it. All this is from your textbook. So each slide, when you watch, you have to thoroughly go through it, because I cannot take it directly without the board. So you have to very keenly watch the video and then understand the concept. Any doubts, we will discuss.